Okay, so let me say before I begin that Katrina and I have been working on this construction, trying to make something that actually works, and we've got all details completed. We haven't quite finished that project yet. I mean, what I'm going to say, but we've definitely got what I'm going to say. It's almost finished. And there are, of course, many other ways of doing this. And we've made some choices that we can make consistent. And of course, there are other ways of defining what we're doing. But we're going to try and finish this one first before we think of other things. The other thing is that Helmut asked me to mention his student, Du Yang, who is building Kuranishi structures from polyfold theory. And so he is actually using a slightly different notion of a Kuranishi structure. And he avoids a lot of Hausdorffness problems because he's assuming he's using polyfold theory to build it, and so he's assuming he has a very nice ambient Hausdorff space that everything can be embedded in, and so he uses that. So his method is slightly different from ours, but no doubt when you look at it, they'll be equivalent in some way. I mean, if you did what we did, putting in more polyfold results, then you could probably get something equivalent to his. But I haven't quite seen the details of his construction, and we haven't quite finished ours, so that's something for a little later. Anyway, what I wanted to tell you now was more about sort of the topological side of Kuranishi structures. So remember what I was defined yesterday. Our Kuranishi structure was a family of charts, which I'm going to write as Ki, where I, and then we've got these transition ij for I, for I sitting in this set I, K, which are just certain subsets. These are certain subsets of our 1 to n. And then we have transitions when I is included in J. And if I is equal to J, these maps are the identity. So we have a family of these charts satisfying certain conditions, and they're subordinate. Each Ki has footprint Fi, and these Fi's, the union of the Fi's are X, and these K big I's then have footprint F big I, which is the intersection of the F little i's for I and I. And actually, once we've chosen our basic charts, a covering family of basic charts, and we've made them all disjoint so that they can be summed, then the construction of them, of the Ki's and the phi ij's, is essentially canonical. The only choice you have to make are what are the domains of these charts. They have to be, these charts have domain. Remember, each chart is a ui, an ei, an s, and which is our section, and a psi, which is a footprint map. And we could all label it all with i's. We're going to we're going to choose the EIs to be isomorphic to the sum. And so they're sort of determined if this is a bundle, so if everything is disjoint. And the only choice in this is really what is the neighborhood UI. This has to be some neighborhood of the footprint in there. And then for the transition functions, there are sort of natural inclusions when you increase I to j. And again, the only choice is that the domain of this map phi ij is what we call uij, and that we have to choose at some neighborhood of the relevant part of the footprint. It's a neighborhood of what we call psi I inverse of fj. So there's really not too much choices, but not too much, yeah. So then we have, if we can do this, if we have a situation where because a Kuranishi structure, of course, could be arbitrary, not necessarily given by our construction. And if you have an arbitrary Kuranishi structure, if the EIs are actually isomorphic to the direct sum, so if EI is isomorphic to the direct sum of the images of the phi i's, I in I, EI, then we say that K is additive. So that's a very important condition for us. And the other condition I explained to you yesterday was a condition called tame, which is a condition on all these domains. So it says, for one thing, that we have uij intersect uik is equal to uij union k. That's going to be true whenever I is sitting inside j and k. So these are the parts of the domain of ui which can be mapped to fj, and these are to the chart over j. These are the parts of the domain that can be mapped to fk, and we ask that their intersection can be mapped to I of j intersect k. Right. So this is true on the footprint level, just arbitrarily. And we're asking it to be true on the domain level. So that's one thing. And then the other thing we're asking is something about, we're asking that phi ij of uik, we're asking that we can control this. And this is going to be true when I is included in j is included in k. And we're asking that this is going to actually be equal to ujk intersect sj inverse of ei. So it means that if we're starting in I and we can go to j, but we know the point we start at actually also goes to k, because that's what it means. We're starting at a point which is here, but it can go to there. Then we're asking that when you put it in here, it can also go to there. That's what that inclusion means, right? So that if it goes there and goes there, we can push it forward. And then what this condition means is we know from the fact that these phis intertwine with S, that the image of this map has to, because all the elements in UI, their sections take value in EI. When you push it forward, the pushed forwards object, the value of their section has to take place in the push forward of EI, which I'm just calling EI again. So we do know that this side has to be contained in that side. And what this is telling us is that uj, this is giving us a restriction on the size of uj. It's saying that uj is not too big. And in fact, we could always arrange that this be true by just removing all the bits of uj which lie in the set sj inverse of ei, but are not in the image. So we can just, we can just cut down to make this statement true, at least putting that, well, we have to also cut this down. So it's a slightly, it's a sort of joint thing. Anyway, so the, yeah?
I think it might help people to mention that the conditions 1 and 2 are things that are naturally true on the zero sets.
They're definitely, yeah, they're absolutely true on the zero set, yes. I've pointed out that that's true on the zero set. And if this is the zero set, then this is just saying it takes the footprint to the footprint. Or at least, well, actually, that's not completely true. Because EI would have to be, if I would have to be empty, right? I mean, EI is a bundle, and thus I is the empty set. So it's not quite true to say it's true on the footprint, but it's an extension of what's true on the footprint. Okay, so then we had theorem 1 was that if K is tame and additive, that implies that our Kuranishi neighborhood is Hausdorff, and that these projection maps, because there's an obvious projection map from UI to K, perhaps I should remind you what this set is, I'll do that in a second, that this is a homeomorphism onto its image. So let me just remind you that this set K, which is meant to be our sort of nice neighborhood of X that we're trying to build, this is just gotten from the disjoint union of all these domains, quotiented out by the relation that's given by, it's a relation generated by all the morphisms. And it's actually, if you take things satisfying these compatibility conditions, then you can construct examples where this map isn't even injective. I mean, it's not too hard, because you really only have conditions on what these how these maps, phi ij, how they behave on the footprint. So on the footprint, we actually know that x, we always have a map of x into there, which is a homeomorphism onto its image. But this could be messed up. You see, this is given the quotient topology. So it means that this map is continuous. It doesn't have to be 1, 1, but even if you arrange it's 1, 1, then there's another problem that if you have an open subset here, how do you know it's open in there in the quotient topology? That's a question of sort of, you have an open set here, you look at its image here, and why that's a problem, partly, is because you have to, oh God, how do you stop this? You have to remember that our images, here is UI, and then here is UJ. So UI is sitting inside there, right? UI is sitting inside there not as a closed set, but as some submanifold. And so we've got an open set here. It then goes to some set which is relatively open in the image, but you have to choose some neighborhood of it. You have to thicken it up to get an open subset of the image. And then you have to make sure you can choose this thickened neighborhood in UJ, so it's sort of compatible with all, and you might have to thicken it up more as you go on. So it's not completely obvious. If you just take a naive point, we've got an open set here. We want to construct an open set in here whose restriction to the image of UJ is the given set. It's not completely obvious how to do it, and it took us a little while to make that construction. Now, I'm suddenly not going to, so that's one of the theorems, yeah, and then the other theorem was that if K is weak and additive, this has a tame shrinking. So you can always, I will define, when I discuss this theorem a bit more, I'll give you a formal definition of shrinking. But shrinking just means that you reduce all these domains, the UIs, to make them to UI primes, which are precompact in the UIs. While keeping it additive? Well, additive, yeah, that will certainly be always additive. You won't change the bundle. So all you're doing with shrinking is changing the domains. But what you're doing is changing the domains to make it tame. And then the claim is we build a cobordism theory and show you that any two of these are cobordant, so you get a well-defined theory. So these are two of the theorems I wanted to talk about the proof of. And then the third theorem to talk about is once you have all this, and so we have theorem 3, then suppose we have this nice, so I'm so far working on the domains, but we have a bundle over it which you can construct in exactly the same way. So this suppose is nice in Hausdorff, it's a nice space. This one is a sort of generalized bundle because at every point here, the points here are equivalence classes of pairs of IX, right, where X is in UI. That's the equivalence classes like that. Over a point like that, you have the bundle, the fiber over that is EI. That's the fiber of this bundle over there. So the fibers are, the bundle has got changing dimensions of that. But it actually, when I was thinking about this, this is almost certainly a polyfold, can be given a polyfold structure, a finite dimensional polyfold structure. So it's got something like that. Then we have this section. And then we want to construct our perturbed section, right? Well, we call it S tilde or something. Our perturbed section, whose zero set we want to be a manifold. And as Katrine was pointing out, there are some issues about how to do that. For one thing, you have to say exactly what you mean. You can't just take any old section. It has to be, you want it to be somehow an admissible one, which is compatible with so S tilde should be admissible. So it's meant to be compatible with the overlap maps. So that if you have a section, if you've got UI and you've got UI and you've got some section over there, and then you map UI into UJ, which remember, this is UI sitting inside there. We've got a section here. You have to say what it does in the normal bundle. Basically, admissible means that in the normal direction, D of S tilde restricted to the normal direction is equal to ds restricted to the normal direction as a map to the quotient of Ej divided by Ei. So when you go from here to here, your dimension goes up. We have a ds, we know, that was our assumption, that ds gave you an isomorphism from this normal bundle to that quotient. And we're asking that our section, actually, when you restrict to those directions, exactly equals that there. Now, this is a condition which is certainly in Fukai Ono in some version or other, but I didn't think it was completely correctly stated. But I mean, it's certainly an adaptation of a condition they have. And so that's an admissible section. And what that means is that if you have an isolated zero, suppose you have, suppose EI over UI, the dimension of your moduli space is 0 or something, you've got an isolated 0 there. That's going to go to an isolated 0 for S tilde here, and it's going to be transverse, because in the normal directions, it's just going to cover the cokernel. So it means that you don't, when you're going from a smaller dimensional space to a larger dimensional space, you might think, okay, the 0 set here is going to be something which cuts this transversely, but that's just wrong from a dimensional point of view, because we're always assuming that the dimension of our Kuranishi structure is the same, and the dimension of the Kuranishi structure is the dimension of the 0 set of a transverse section, because it's the dimension of the U minus the dimension of E, and that's fixed. So if you have a 0 here, it'll remain an isolated 0 there, or whatever you have here will remain there. Okay? So then you have this idea of an admissible section, but then there's a problem of how you actually construct sections, because you see, if you think of your footprint, here's Fi, F1 say, and here's your footprint F2, and here's the overlap F1, 2. Suppose you make, people often do this by doing some kind of partition of unity. I mean, you take a section over here, or, you've got UI, you've got UJ, you've got a section over here, which you can cut off, which is going into EI. And then you want to transform that to a section over here. Well, you can't just identify that. Well, there's this problem that we were pointing out before, that in this space, you've got the image of UI. This is, you say, U1, 2. You've got the image of U1, but you've also got the image of U2, and they intersect non-transversely. So if you have something defined on U1 and you have something defined on U2 intersecting non-transversely, however smooth they are, they may not have a common extension. So it's smooth extension. So what you have to do is you have to reduce the cover, so that you never are in a situation where you've defined something over F1 and F2 and have to make them compatible. What you do is you reduce this cover so that you, instead of having a cover like that, you have a cover which has that, and has that, and has this. So this is V1, this is V2, and that's V1, 2. So I sits inside Fi. But V1 and V2 don't intersect. So you have that Vi intersects Vj if and only if I is contained in J or J is contained in I. So you've really, and there's a standard method. Actually, this idea comes from Liu and Tian. This is reducing a cover like that, so it makes it possible to construct things. So it means on all the sets you can construct by induction on the length of the set I. So all the sets of length 1, they don't intersect, so you just construct your section. Then you look at all the things of intersection 2, at length 2, and you can build on that. And they're all disjoint again, and so on. So it gives you a nice, it sort of separates everything out. It's sort of like taking a covering of a simplicial complex by stars of the vertices and replacing it by a covering by the stars of the vertices of the first barycentric subdivision. I mean, that kind of trick. I mean, it's exactly that. So it just makes the construction of sections much easier. And I haven't actually written out all the details of this, because you see, you need a lemma that says if you can certainly do this on the footprint covering, but then you have to say, okay, suppose I can do this on the footprint covering. I can find a compatible reduction of all the domains so that I can do this on my space K. And I haven't written down the argument. I just didn't have time to think about it carefully. But it has to be true. I mean, I can see no problem with it. It's just that it's not completely written down. OK, so that's all I'm going to say about the sections. I mean, you just, yeah. Theorem 3 is, OK, what is Theorem 3? The theorem, yeah, I didn't say that. Given that you can always find admissible sections which are transverse to the 0 set. And, well, I mean, that's during the construction. And actually, let me state Theorem 3 carefully. OK, Theorem 3. Given, you know, a Hausdorff, a nice epsilon over K, there exists a shrinking K prime, say, so that's going to be sitting inside here, and it's going to have the property that if you look at K prime, it's going to be sitting, this is the closure, it's going to sit inside the closure here, inside there. So this closure is compact. So you can, and so you've got the shrinking, and then you've got the restriction of your bundle. This is just a restriction of the bundle, so that you have a transverse section S tilde. You can find an admissible section transverse to the 0 set, so that the 0 set of S tilde lies inside K closure, or the interior of that. Perhaps I should even say it's lying inside the interior of that. So that means that this 0 set, it's locally smooth, and it doesn't have a boundary. It's compact because it's sitting inside some compact thing. So that means that that's a manifold, Hausdorff. And that's going to be, and again, you can show the cobordism class if this is independent of choices. So that's going to be the sort of local model for the Kuranishi, the virtual moduli cycle is going to be represented by this 0 set. Okay, so that's Theorem 3. And yes, before I was just telling you how you construct it. You refine this cover, and you just then can work chart by chart. Okay. So we've got these two other theorems to prove about how you prove that this is Hausdorff and how you, and so on. So let's see. Okay, so there's an important, I'm not going to give you all the details, but let me just sort of show you what goes behind it. So we define we write Ix for the elements. These are a typical element in this unit, which are the domains of our Kuranishi chart. And then we're going to say that Ix is less than or equal to Jy if there exists, basically if I is contained in J and phi ij of x is equal to y. So in other words, if there's a morphism, a direct morphism from here to here, we're going to say one's less than the other. So then our equivalence relation is basically generated. You know, we know that Ix is equivalent to Jy if we have some chain like Ix is equal to I0 x0, and that's less than or equal to I1 yx1 bigger than or equal to I2 x2, and so on. Right? You have this chain and ending up with IY, some finite chain which goes up and down. Yeah, but we're not allowed to invert morphisms. Right, right. And if you have two, you see, because of our composition, if we have two symbols like that, we can concatenate them. So if I is less than or equal to J and J is less than or equal to KW, then I is less than or equal to JW. So we know that then any equivalence is given by some going up, down, up, down, up, down, up, down. Okay. So then the lemma is, I mean, the sort of crucial lemma about why this theorem holds is that if k is additive and tame, that implies that ix less than or equal to jy, if and only if there exists a z in ui union j such that we have ix less than or equal to I union j z bigger than or equal to jy. In other words, we can shrink the chain to three things. And it's also going to be if and only if. So that means we can go up and then down, but it's also true that we could go down and then up. So that it's going to be true if and only if there's a w in I intersect j such that ix is bigger than or equal to I intersect j w less than or equal to j y. And so that means that we have a lot of control, a sort of direct control of our equivalence relation, because we don't have these chains going on that could do all kinds of complicated things. Tame, what's these two conditions? Still there. Well, let me give you the beginning of the proof of this. Okay, I'm not going to prove the whole thing, but let me just okay, so so what you want to do is, first of all, is you want to prove that these two conditions are the same. So you want to say that if you have that ix less than or equal to I union j z bigger than or equal to jy, there exists a w in ui intersect j such that ix is less than or equal to I intersect jw greater than or equal to jy. So that's saying if you're going from here up. Oh, right. Okay. Yes. Then you can go down. Right. They are the wrong inequality. You want to be able to go down and then up. So it's saying going that is the same as going that. And then you can see immediately, if you have something like that, you can immediately shorten a zigzag like that. I mean, if you have a long zigzag, that, I mean, we prove this implies this, and we also prove that this implies that. Right, so but I'll prove one of them for you because the arguments are exactly the same. But if we know that going up is the same as going down, we can replace that by going down, and then we can just go replace it by one thing. So we can shorten the chains because we're allowed to compose two downs or compose two ups, because we were assuming that's our co-cycle condition, that we can do that. Okay, so this is basically, I mean, if you do this and it's converse, then it's sort of immediate, this thing holds. So how do you prove this statement? Well, you just do it sort of in the obvious way. Well, what do we know about z? We know that z sits inside, well, it's an image of this thing, so it sits inside phi I union j of I union j. Let me write k instead of I union j, so I don't have to write this all the time. So k is equal to I union j. And let's make h equal to I intersect j. So that we've got intersect phi I, j k, u j k. That's what our hypothesis is there, right? And then what do we say? we use this second condition telling us what this image is. See, that's why we need our second condition. Our second condition tells us what this image is. And if you look at our second condition applies for I included in j included in k. But if j is equal to k here, it says that phi ij uij is equal to ujj is just uj, right? So we can forget it. It's just equal to sj inverse of ei. That's what it says when I is j. So that means that this is sk inverse of ei intersect sk inverse of ej. But now we have additive property so that these two things are the same as sk inverse of ei intersect ej. Which is I intersect ej, which is what I was calling h. And now we know that's the image of phi I of hk. Right? I mean, just using this again, we know if we can say what s takes, the whole idea is if we can say what value s has on a point, we know that it comes from far enough down. So you can see that's the essential thing. That then the point in here is going to be our point w. Right? So that means that if you start with a point here, you can find a point w, and then of course there's a little bit of checking to check that it's all right, but that's the idea. So in fact, we're using to prove this, we're really using 2 only. We haven't used that very much, but perhaps one would in another bit of it. Anyway, we just use this condition with j equal to k. To say that, I mean, what this is telling us is that we know what the image of phi ij is in uj. That's the information. So that's why we can prove a lemma like this. And once you've got a lemma like this, then, well, of course, there's more work to be done. Well, I showed you could use this lemma to shorten these chains. And once the chains are really only of length 3, when you go from here to here to here, say, then it's pretty easy to prove that things are Hausdorff and the Hausdorffness. To prove it's Hausdorff, you need to show the relationship is closed. And it's not too difficult to do that. I'm not going to spend time doing that now.
And the problem with unboundedness with not length 3 changes that you might become longer and longer.
I think it was a problem with longer and longer ones. Let me just have a look and see whether I had to do it. I don't think we had to do a shrinking of this. I think we just did this. Yeah. I don't think I'm lying. Let's see what it said. Well, what I definitely claim here is that the statements I gave you are correct, and that it's easy to prove closeness when you have these chains like this. Okay, so then there's actually a little bit more to do to show that these, I mean, we're trying to prove not only that this is Hausdorff, but also more to do to show that these maps are injective. So I wasn't going to go into that very much. But really, again, this lemma is absolutely crucial. I mean, this lemma, it's pretty easy to see that it implies that K is injective, that these maps are injective, and then you have to construct this open thickening, this open set. Okay, so then the question is, how do you actually construct something which is tame? Okay. Well, this is not coming down. Why is it? Oh, God, this way. I can't. Oh, here. So for theorem 2, well, we have to construct the shrinking. So first of all, we take our cover Fi. Yes. So what a shrinking is, first of all, you shrink this to Fi prime. So this has a property so that it's still a cover, that Fi prime closure is sitting inside Fi. So it's still an open cover. You've reduced all the sets so that the closures sit inside there. And we also want to not reduce too much, so we want Fi prime, which by definition is just the intersection over I and I of F prime I. We want this to be non-empty if Fi is non-empty. So they have the same intersection pattern, they're just all slightly smaller. So we shrink the footprints, and then a shrinking of K is some family of charts where we have these sets Ki prime and the phi hat ij with the footprints are the Fi prime, so they're corresponding to the shrunken cover, and the domains Ui prime are sitting inside, they're precompact in Ui. So these are the domains of Ki. So we just shrink all those domains. And then all the other information, we take U prime I j to equal U prime I intersect U I j. That's what we do. So we just, and then we just do everything by restriction. All the maps are just restricted. And that'll give us a weak. If we start off with something weak, which means that the cocycle condition, it means that composites are sort of, when the cocycle condition was phi ik was equal to phi jk phi ij when both defined. That was a weak cocycle condition. If you shrink all the domains, you'll still have a weak cocycle condition. And this will have the right footprint because the UIs had the right footprint, right? So this has footprint Fi prime, and so this is going to be okay. Actually, looking at it, possibly it's conceivable one might have to do a little bit more than that. Perhaps one has to put it contained in that, because we may not want it exactly equal to that. We just want it to be some neighborhood, but we can just choose the neighborhoods at will because we're not. We just need it. We just need U ij prime intersect Si inverse of 0 to equal the psi I inverse of F j prime. We want to have the right footprints. Anything with the right footprints, and as long as it's sitting inside here, that will be fine. So then, right. So then, how do we tame this thing? So the taming conditions, remember, we had conditions Uij intersect Uik equals Uij union K. And so we've got this condition plus the second condition, but this is the first taming condition. So we construct the taming basically by induction for the sets U, I, J by induction on the length I. So we first do it for all the sets U of I of length 1 and all j. And then we do it for the sets of length 2 and all j, and so on. So if you think what we have to do, suppose we start off with U1. That has got sitting inside it. Suppose we've already shrunk things. So this is already pre-compact. So this is shrunk, right? So I don't need to already shrunk. Don't need to say anything more. We've got U1, which is pre-compact in whatever other domain we had. And we want to construct inside there a bunch of sets U1j, which satisfy this taming condition. So that U1j, that they have to satisfy that taming condition. They have to have the property that U1j intersect what I'm going to call Z, which is S inverse of 0. That's got to equal what I'm going to call Zj, which is psi inverse of Fj. So I suppose I've shrunk. So this is, I could have put a prime in there if you like. This is the shrunk domains. So I need those things to be satisfied. And I also need U1j. Perhaps I should say, I want to find these new, let's call these new sets double prime so you're not confused. These are the new sets I'm trying to construct. I want these U1j double prime. They've got to be subsets of the U1j. Because this is where our phi ij are defined, and we've got to have them so that the phi 1j is defined there. So we need that. So we have these conditions on our set. So we have a set U1. We have inside it the 0 set, which we can think of as Z. That's the inverse image of the footprint. We have a bunch of these sets, which I'm going to call Wj. So these are sets Wj. The point about these Wj's is that Wj intersect Z is equal to Zj. Right, because these things have the right footprint. So we have, say, a set, we have a bunch of that set and that set. I mean, they're sort of nested, right? We've got these sets. We've got the Wj's, which intersect. So W, one of them is like that, and the other one is like this. So this is say W2, this is W3. And this is W, and then on the overlap of these two sets, we have a W as perhaps a different set, which I'll put in blue. We've got some different set, completely W23. We don't really have any good relation between these W's. These are just the domains of our maps, and they're just, all we know about them is that they intersect our 0 set nicely. That's all we know about them. And so we've got to pick out from those some sets U double prime ij, which have this nice intersection property. That's what we have to do. So there's a lemma which says, I mean, this is sort of the crucial lemma, which says you can do this. And which explains why we needed to shrink. So let me state that lemma. So we've got U, which I'm just going to take in RK, but we could be more fanciful. It could be a metrizable or a normal space or something. But anyway, just take an open set in RK. And let's see, where can I find this lemma? Yeah. U prime sitting inside U is precompact. We've got Z sitting inside U prime, which is relatively closed. So that's our 0 set. U prime. No, precompact in U. So the closure of it, the closure in U. Because we don't really have RK here. We're just sort of thinking. Anyway, so we've got Z sitting inside U relatively closed. we have these open, relatively open sets, Zi, sitting inside Z. So they're relatively open in this closed set Z, and we define Zk. We define that to be the intersection of the I and K of Zi. So in the example, Z is a 0 set, and these sets Zi are these sets Zk are the intersections of our, these are just correspond to the footprints Fk. Because that's all in the footprints. We have these sets Wk, which are open in U and have the property that Wk intersect Z is equal to Zk. And then the claim is, and so these W's K's have no nice relation to each other. And the claim is that there exist open UK, which have the property that UK is in WK, that UK intersect Z in the set ZK, and they have this nice intersection property that UJ intersect UK is equal to UJ union K. So in other words, the nice intersection property that we have on the footprints, we can choose a consistent set of neighborhoods so that it has that property, and moreover, we can choose a consistent set of neighborhoods sitting in our arbitrary sets WK, which we know very little about. I mean, they could be arbitrarily, if you just take an example where, this is your open set ZK, and WK sort of is rather small, so you want something in there. It's not so obvious exactly how to do it. But Katrina and I did find a construction which works. I mean, it's very elementary, but it uses upper semi-continuous functions or lower semi-continuous functions. I mean, it's not totally trivial that we could find a construction that worked. But anyway, we did that. Oh, yes, of course, it was wrong several times. That goes without saying. And, of course, the other thing is what was wrong more than several times was putting everything together. I mean, at each stage, there are lots of little choices you can make. And if you take a wrong path at some point, it becomes very difficult. But if you choose a correct path, then you can do the things. So, actually, that was probably the hardest thing. Anyway, you see, this lemma basically tells you that you can do the taming on the sets U1 when you only have conditions on the things going out. And then suppose we look at the set U2, U1, 2. So we look at a set UI with I equal to 2, length of I. So then we've got things coming in. So we've got, U1 and U2 all get mapped into U1, 2. And so we want to apply this lemma again. And this is where the tameness comes in, because you see this lemma, what's crucial about it is that we sort of say we have a set where we know what on the footprints everything is nice. We have our intersection property. Now, when you go up to level 2, what set is nice? We don't want to affect, the idea is we've made all our choices of UIK with I equal to 1. And we don't want to change any of those choices. So that means we know what all the images of those sets are, right? We know, did I destroy the taming conditions? Well, we had UI intersect UI, well, we had these intersections UIK is equal to UIJ intersect K. But then we had the second set of taming conditions telling you what happened to these sets under the, this was UJK intersect S inverse of EI. And we don't want to change these sets. These sets are given. UIJ is, if I has got length 1, that is given. That is given, because we're just doing it by restriction. So this set is given. So what we have to choose, so perhaps I should have said, I suppose that we're trying to work on a UJ with J being 2. So we're assuming we're trying to find the things. I has got length 1, so J's got length 2. Inside UJ, we can choose this one. If J's got length 2, This is what we're now trying to choose, all these sets. But we know what the intersections have to be with S inverse of EI from this, E1. So what our set nu Z is going to be the union. So Z for, say, Uj is going to be the union of all the H less than J with H was H strictly less than J. I mean, in general, this is what's going to be. And then we take the images of all these phi I H J. Well, actually, no, we don't take the images. We take the S J inverses of the EHs. That's our set. And the set ZK are going to be the intersections of Z with our, oh God, what are they? I think the sets ZK are going to be, I haven't actually, I mean, we've got it all written out in beautiful detail. I didn't, but probably it's going to be the union over the H less than or not equal to J of these sets phi H J of U I K. That's what our ZK is going to be. And by definition, ZK is going to sit inside Z. So these are all the things we've already chosen, right? Because we've already chosen, this is an H. So we've already chosen all these sets UK. H has got length 1, say. It's less than the length of what we're trying to fix now. So these we know, this set we know, and that's our ZK.
So in your lemma, that would correspond to the Z sub I, because it was a Z capital K in your lemma.
Well, our lemma, oh, well, ZK, well, the ZIs would be, right, so the ZI would be, well, it would be this, but UK would equal H union I. Right, if you add one more on. Yeah, there. So the labeling's slightly off. But you sort of see the idea. The idea is that we sort of got up to a certain level, and we make our Z's. And these are really, you know, Z is relatively closed, and these things are relatively open. So and then we can apply our lemma to choose our set of domains, and then we continue. That's the idea. But you see, it's absolutely crucial that we have this condition, so we can sort of figure out in our set U, if we've got a set Uj, you know, Ej is the sum of Ei with I in J, and that gives us a sort of stratification of Uj. Which of the bits, you know, look at the section S. What is S inverse of all these things? And that gives us a set there. And we use that as a guide when we're doing this argument. So just a question, I mean, once you've got the lemma is sort of hard, slightly hard to prove. I mean, it must be known, but certainly we couldn't find a proof of it anywhere. But this is just a question of ordering things properly, just a question of, you know, choosing things in the right order and doing some kind of inductive argument, checking at each step that you've got everything right. So that's the idea of how you tame it. You just sort of start at the bottom and you tame and go up.